see. Okay, so as usual, if you have any questions or anything is unclear, just interrupt me, and then we have time to go through all the details. So now today is the 9th lecture, and we have a total of 10. So we have 3 hours today, and then 3 hours on Wednesday. It may be so that there's a little bit left, maybe, I don't know, half an hour or so, and we have one more meeting scheduled. I think it's in a week or so, something like that. And I would just use that time to wrap up everything rather than now try to squeeze everything in. I guess it's better to, you know, treat everything in the proper way. So don't hesitate to ask questions if anything is unclear. We have time. We can kind of then just adapt it towards the end. Okay, so today we're going to talk more about stability, in particular the stability of viscous shear flows. So essentially we will end up with what is called the Orr-Sommerfeld equations, and we will actually apply them to channel flow. And I have some MATLAB demonstration where you can actually see how we can use these equations to get real solutions in channel flow. But before we do that, which will be the main part of today, but before we do that, as usual, I would like to summarize very briefly what we have done so far. And of course, the main thing that we're talking about is stability. I'd just like to remind you again what the basic idea really is. So we distinguish stable from unstable flows in the sense that in a stable flow, whenever you have a flow state, which may be, I don't know, the Poisson profile, so a certain velocity profile, and if you start to disturb this flow, so you hit the flow a little bit, there's a little bit of noise, maybe some vibrations, maybe some surface roughness, and the flow is then determined called to be stable if the flow goes back to its original state. On the other hand, the flow would be unstable in this situation when you start to disturb the flow a little bit, and then it would just go somewhere completely different in phase space. And of course, the main different location in phase space would be that it goes from the laminar flow to the turbulent flow. And of course, that's what is most important for us from an engineering point of view, because we would like to be able to determine when we have transition to turbulence. And transition to turbulence is always initiated by an instability somewhere in the flow, so something that is growing, departing away from the laminar state. As we have seen in the examples that, the videos that I showed you, I guess, on Thursday last week, you know, these wavy-like disturbances that we had, which then grew, and then at some point they were large enough to actually initiate turbulence. So that's the reason why we're also interested in that. So stable and unstable, I guess this is pretty clear what is meant. Unfortunately, maybe the most common state is a little of a fluid flow is a little bit more complicated. That would be this conditionally stable situation. Now I don't know, I'm drawing here, but it doesn't change anything. We're not connected anymore. It says I'm offline, okay. The EduROM is not extremely stable. Sorry about that. I need to reconnect. Hopefully it works. Okay. Rejoin. Okay. I'm online again. Okay, that didn't work. So, I need to share the screen. Okay, I'm sorry about that. That works. Okay. Anyway, so what I was saying is that the most common state is, of course, the unconditionally stable case, where you have a mixture between stable parts, and then if you amplify or if you hit the flow sufficiently large, it will go to another state, and so on. Now, the way that we proposed last time how we could analyze stability of a flow is to go via very small disturbances, so infinitesimal disturbances. And the motivation for that was that on the one hand, we can then linearize the equations and get a linearized evolution equation. So we define a base flow, a base state, then we linearize it about the space flow, and then we could determine eigenvalues in frequency domain, where we could see whether something is exponentially growing or exponentially decaying in time. So we then can talk about a growth rate and an angular frequency of our eigenvalue. So that is the first motivation why these infinitesimal disturbances are important. The second reason why this is important is, I guess actually I have it right here. The second reason was the fact that when we looked at what actually makes something grow in a flow, we realized that there is always a balance between production and dissipation. Mute. This one? Okay, good. So we saw that there's always a balance between production and dissipation in a flow. Actually, the importance of this is that both production and dissipation actually originate from linear terms in the Navier-Stokes equations. The nonlinear term, so the advection term, resulted in a triple correlation, which we could neglect because it was a divergence term, because it was a transport term, because of the conservation properties of the Navier-Stokes equations. So that means also from just kind of an energy perspective, we realize that small perturbations, infinitesimal disturbances, are very relevant in order to understand growth mechanisms in the Navier-Stokes equations. Okay, so we talked about this, and then we, of course, started to focus more on the Navier-Stokes equations. So we have here the Navier-Stokes equations, and what we introduced into those is the typical decomposition of the velocity into a base flow and a perturbation. And that was the last thing that we wrote down last time. We actually had the perturbation equations where we split everything to base flow and these primed quantities. And now our job for today is to apply these, or apply some simplifications to the perturbation equations such that we can start to make sense out of the various solutions that we get from them. The picture that we would like to have at the end is something that I have drawn here. So we would like to determine stability as a function of a perturbation parameter. In this case, it would be as a function of the Reynolds number, or the viscosity, if you wish. And what we have also discussed on Thursday was that there is essentially three different regimes. We have regime 1, regime 2, and regime 3 here, going from unconditionally stable via conditionally stable to unconditionally unstable. And now, with the tools that we have introduced so far, we have realized that unconditional stability would mean that there is no energy growth. So everything that I have in terms of disturbances would just decay over time. And of course, this is for very low Reynolds numbers, so very viscous flows. And this stability will then be determined by the Reynolds Bohr equation. On the other end of the spectrum, we have the unconditionally unstable region, where we said that this is really what is determined by these eigenvalues that we talked about. So this region here, everything above Rho C, the critical Reynolds number, would be the region where you have an unstable eigenvalue, you will have exponential growth of your disturbances. And then we have the second region, which we'll talk about next time. Yeah, essentially this is where we are in terms of our analysis. What we then also wrote down at the very end of on Friday was the topic of today, namely viscous stability of shear flows, and we kind of explain what we mean with all these words. Viscous means we're somewhere at finite Reynolds number, so we're somewhere along this ray. Stability, of course, in the notation of today, we're talking about linear stability. So you would like to look at something that is linearized. And then shear flows, what I mean there is that the base flow has a certain derivative or has changes in at least one direction. So there is shearing action going on, which is the main or will be the main driver of our instabilities. And these were concepts from the beginning of the 20th century, when people started to realize that we can actually use linearization mathematical tools to analyze these types of flows. Also here, maybe I will show you some slides later on also on the historical perspective, but it's important to realize that at the end of the 19th century, so I think it was 1886 or so, when Reynolds came up with his high flow experiments, and not much later it was Rayleigh that, Lord Rayleigh that did inviscid stability analysis. So he neglected the viscous term and could see that under certain circumstances an inviscid flow, so an Euler type of flow, would actually become unstable. But it then took a few more years until the viscous stability came in, and it turns out that viscosity actually plays a very important role in the instability. So from a practical point of view, it was extremely important to have the viscosity as part of the solutions. But anyway, that's now what we're going to talk about today. We will make a few more, or actually just one more assumption, and in order to proceed to make things a little bit simpler, and that is what we will call the parallel flow assumption. The parallel flow assumption essentially just means that the base flow is a little bit simpler than it could actually be. We just say that the base flow has just one velocity component in the streamwise direction, and the variation is just in also one coordinate direction. So essentially what it means is if we have a coordinate system, something like that, where we have x, y, and z, we say that our base flow that we're going to look at will be something like that. So there will be no variation of our base flow in the x direction, and no variation in the z direction. The only variation of the base flow is in the vertical direction. That is obviously what is called a parallel, or this will result in a parallel flow because it will just be flowing parallel to the xz direction. And it will, of course, make our analysis simpler because many of the derivative terms will actually fall out. So we will not have so many terms in the end. But at the same time, this, of course, it still allows quite some complex flows. So just think of the various flows that we talked about in this course so far. So, for instance, Poisson flow, so channel flow, is of course part of this. Couette flow is also a parallel flow, so we can treat that. Boundary layers is of course a little bit different because in reality a boundary layer would grow. You know, we derived that's the square root of x. And that, of course, means that with the parallel flow assumption, we're kind of, making the boundary layer parallel. But again, you can now think of the boundary layer approximations where we said that the streamwise variation is much, much slower than the vertical approximation, the vertical changes. So therefore, maybe approximating a boundary layer with a parallel flow is not so bad often. Okay, so So we make this parallel flow assumption, and now I guess it's time to actually see what happens to our linearized equations. Linearized equations for the perturbations. And that's essentially just taking the Navier-Stokes equations that we derived last time and just plugging in this specific form for the base flow that we now set. And in the end, what we will get is the following. It's duy dt, which is equaling minus uj duy dxj minus uj duy dxj minus dp dxj plus 1 over Reynolds d squared ui dxj dxj, and then we have to continue with the equation dy dx xi being 0. So for the time being, these are still the general equations. What I have done here, I have actually dropped all these primes here. Now, typically there should be primes because we're looking at the disturbance, and the base flow is the capital letters. But for simplicity, from now on, I will drop these primes. And again, I'm not just doing that here. This is common in the literature that at some point when you start to write down the disturbance equations, you start to neglect the prime. So, as I said, now the issue is we would like to introduce the base flow. Yes?
How come we neglect the prime?
Just from notational simplicity. So it's not that I'm neglecting, I mean, it's still the disturbance. It's just, I just say that, when you would originally, our formulation was this, that we said, we wrote like this. But now we understand when we write the disturbance equations that we only have this and this left. And therefore we neglect it. But of course it's important to remember that we're still talking about the disturbance. It's not the full velocity. So perhaps maybe it would be better if this kind of had a different notation. But it's, as I said, it's common in the literature. The reason actually is not just laziness. It's also because you can realize, of course, that now the base flow, because it's only a function of one variable, the derivative of the base flow can then be written with a prime. And if you would keep the primes here, then you would mix up the primes from the disturbance with the primes from derivative. Okay. Yeah. So what we would like to do now is to introduce the base flow, and even more so, we would like to write the equations in such a way that we can do an eigenvalue analysis. So the goal here, is the following. Write these equations, in the form which looks like this. dq dt is some matrix or some operator times q, because this is the way that we have written it before when we looked at our little analytical problem, where we could then formulate everything in spectral space or in frequency space as an eigenvalue problem. But now we would like to write our Navier-Stokes equations in this way, so that we can actually feed it to an eigenvalue solver and get the proper stability equation. The problem, I guess, as you can directly see, is this term here, the pressure term, which then together with the continuity equation somehow forms this, constraint on, that the velocity needs to evolve on a divergence-free subspace. So we somehow need to deal with that. So the problem really here is how to deal with the pressure, as always in incompressible flow, essentially. Right. So how do we do that? So the first step now would be to, as I said, write the equations in the specific form that is suitable for the base flow that we have. So the disturbance equations are then the following. I'm writing now the three equations for the three velocity components. So I go from vector notation into normal notation, because in that way we can directly see what terms actually fall out. So in the streamwise direction, we will get minus ub du dx minus ub prime times v minus dp dx plus 1 over Reynolds of nabla squared times u. In the v direction, it would be minus ub times dv dx minus dp dy plus 1 over Reynolds nabla squared v. And in the w direction, so in the z direction, it would be minus ub dw dx. Then we have the pressure, dp dz, and the viscous term. And then, of course, continuity is just the same as before. Du dx plus dv dy plus dw dz. So now what you see here is that because of the specific choice of our base flow, so that the base flow is only a function of y, and it's only in one component, a lot of the terms from the convection have actually disappeared. So that's the power of doing the parallel flow as such. The other important thing is what I just mentioned before. This prime here is now a derivative. So this is actually dub dy. So this prime is not the disturbance prime anymore. Okay, so this is now our equation. This we would like to solve for our solutions or our perturbations, which we would like to solve for, the vector u or ui, which is just u, v, and w. But we have the problem of the pressure. Because again, keep in mind, we would like to write it in this form here. dq dt equaling L times Q. But now we have this kind of weird continuity equation plus the pressure. Now, what does one do in these situations? Essentially, one does whatever one does. If one doesn't know what to do with the pressure, one just computes the divergence of the momentum equations. Because if you do the divergence of the momentum equations, then you will see that essentially the continuity equation will say that all the time derivatives, for instance, will be zero, because you're actually deriving an evolution equation of the divergence. Of the divergence is zero, as we know from continuity. So that's the usual trick when you want to get rid of the pressure. So the idea here is compute the divergence. Divergence of the momentum equations. So that means I'm just doing nabla times dy dt. And this then becomes nabla times minus uj dy dxj minus uj dy dxj minus dp dxi plus 1 over Reynolds of the viscous term, d squared ui dxj dxj. So this is calculating the nabla. So now, of course, I would like to do that for my simplified equations that I have here, the simplified ones where I use the specific form of my base flow. And so that would then give me on the left side something like this, d squared u dx dt plus d squared v dy dt plus d squared w dz dt. I'm writing it in this kind of weird way, so that on the left side I just have the sum, or the divergence here, which is of course the sum of the x, the y, and the z component. So that I can write here on the right side, essentially the divergence of all of these terms independently. I mean, I guess you realize that the divergence equation, of course, in the end is a scalar equation, so I need to add all the components together. So that means I'm just taking or writing here on the first row the x derivative of this one here. In the second row, it will be the y derivative here, and then the third row, the z derivative of the last row. That will give me then the divergence at the end. Yeah, so I just need to do now the x derivative of the first line here, and what I will get one after each other is minus dub dx times du dx minus d squared u dx squared times ub. That's essentially the product rule applied to the first term. Second one will be d squared ub dx dy times v minus ub prime dv dx minus d squared p dx squared plus 1 over Reynolds ddx of nabla squared u. So this is ddx on the first row. Second row, I need to do ddy. I'm simplifying it, or actually the second one I still write. This will be ddy of ub times dv dx minus ub times dv dx dy. Then we have the pressure, d squared p dy squared, and then the viscous term, 1 over Reynolds dy of nabla squared u. Before I write the last term here, let's just see what actually remains, or which terms become zero, because most of these terms actually become zero because of exactly this idea of the divergence. I will directly realize that actually the viscous term is zero because I can directly take in the derivative into the Laplace operator, and then I'm adding all of them, and so in the end it will be zero. So this will be zero together with this, and also the one corresponding to the W direction. So these guys will be zero. If I now start with this term, this is also zero because ub dx is of course zero because we said it's a parallel flow. The second term, where do we have it? Or let's start with yes.
In the last term of the second derivative of v, shouldn't be nabla squared v.
This should be v. Yes, of course. Yes, exactly. This should be v. Yeah.
Professor?
Yes?
In the equation you just wrote, it's minus ub dv over dx dy or dv squared over dx dy.
Which one is wrong?
Minus ub times dv over dx dy or minus ub the second line.
second derivative should be the square.
Yeah, I think it's the second derivative of v over dx dy now.
Here, this one, huh? Or?
Thanks.
Yeah. Ah, exactly. Yeah, that's correct. So if you now continue with taking away terms that can actually fall away, so this one is 0. Then of course this one, this term, which would be the span-wise derivative of the base flow, would also become 0. And then the other terms that will be 0 will be this one and this one and this one. So essentially what remains at the end of the day is the pressure term, which is here. It's this one here, and it will be this term here that is left. Actually, this one will also be 0. So essentially, most of the terms of this one will also go away. With this one, we have also said most of the terms will actually disappear at the end of the day because of the idea that we do the divergence of the equations. Of course, the sum here of the time derivatives will also be 0 because we can just switch the time derivative out. So that means what we have in the end, as a consequence of doing the divergence, is that the only thing that is left is the pressure term plus this one term that comes from the y direction, which can act as a non-homogeneity in the pressure. So at the very end, what we are left with is nabla squared p, which is minus 2 ub prime dv dx. And this is what we will call the pressure Poisson equation. Why is it a Poisson equation? Well, it's essentially a Laplace operator on the pressure, and we have an inhomogeneous term, minus 2 times ub prime dv dx. And of course, I made one mistake. This one should, of course, not. This one should stay because that's the two terms that make it together.
So even the pressure term of the W component.
That will stay. That will stay there. Yes. So that these three terms together, they will then make up the Laplace operator. So the sum of these three terms will be nabla squared p. And the two terms that remain is this one and this one, which then give minus 2 times ub prime dv dx. And all the other terms will. And the reason, I mean, I guess we just said it, the reason for that is that these two, so this one and this one, they go away independently, and all the others go away as the sum of being divergence terms. Okay? And of course, this is a very nice equation because now we have a way of calculating the pressure if we know the v velocity. So if we know dv dx, then we could, in principle, calculate the pressure by inverting the Poisson equation. So that means right now we're in a situation. Now we can remove the pressure from the v equation. Well, why the v equation? Well, because the pressure actually depends on dv dx. So how can we do that? Well, if we look at the v equation, that's this one here. Now that's the V equation. So somehow we need to replace the pressure here with what we have calculated here, to get rid of the pressure. But the problem is, here we have dp dy, and here we have nabla squared, so Laplace p. So of course the easiest is if we just multiply, the V equation with nabla squared. So we take essentially the Laplace operator of the second equation, because then we will get exactly ddy of Laplace p, which is what we know now how to replace. So what we do is we calculate nabla squared of dv dt. So this the V equation, which then becomes nabla squared of minus ub dv dx minus dp dy plus 1 over Reynolds of nabla squared v. So that's just the V equation that I had written here, multiplied by nabla. But now I can take this nabla squared p and essentially put it in here. So what I will get then is, if I just rewrite these equations a little bit, I get ddt plus ub ddx of nabla squared v. So that's essentially taking this term plus this term together on the left side, and on the right side essentially I have everything else left, which is I'll get ub double prime of dv dx plus 2 ub prime dv dx d squared v dx dy plus ddy of nabla squared p minus nabla squared 1 over Reynolds nabla squared v being 0. So what I have now done is I have taken, or I have essentially taken in the nabla squared into the brackets, which gave me another part of this term, which is the ub double square, a double prime. The pressure term I have replaced with my pressure Poisson equation, which was, no, I haven't done that yet, it's still here, sorry. This is still here. So this is the inner derivative of this term. And then I have the viscous term, which I just put the nabla in front. Now I'm sorry. Now I'm in the position where I can replace this with the Poisson equation. So that means everything remains the same for the time being. So ddt plus ub ddx of nabla squared v. So these guys are all the same. But now I can take in this one here, which is ddy, and with a minus sign, because I have a minus here, of 2 ub prime dv dx. So here it is. And then this one, I can rewrite a bit because I can't take the nabla in, so I actually get nabla to the power of 4 of v. Okay? So what I have achieved now is that I have gotten an equation where I remove the pressure, so there's no pressure anymore. But the problem, of course, is because I remove the pressure, suddenly I get a fourth derivative of the velocity v. And of course, the reason for that was because I took the second derivative in order to be able to remove the pressure. So I took the Laplace operation. Now, there's one last step that I can do, because I can realize that if I perform this derivative here, so d dy of this multiplication of ub prime and dv dx, of course, first of all, it's a product, so I get two terms. So I get minus 2ub double prime dv dx. That's if I take the derivative on the first term, and then I take the second one, which is 2 times ub prime dv dx dy. So that's just blowing up this term. And then I will realize that actually this guy is the same as this guy. So that means that, I'm just simplifying it a bit, so if this is the same, this is the same, this is the same, then this is the same. This term will go away with this term. So what I end up with at the very end is that on the left side I have ddt plus ub ddx of nabla square v, and on the right side I have, or write it like this maybe, minus ub double prime ddx minus 1 over Reynolds nabla to the 4 times v. Yes?
Is there supposed to be a square where you cancel out dv?
Yes, it's again. I see mistake.
Did I? Here. Yes. Yes.
Okay.
I'm sorry.
Okay.
I seem to. I seem. Yeah. Of course, that's the second derivative. Yes. So at the very end, you end up with this equation, and this is now one of the major. It's not fully the result that we want, but this is now one of the major achievements, because we have now an equation for v, so the disturbance of v, written, as a function of only v. So there is no pressure anymore. The divergence has been eliminated, and it's just an equation, one scalar equation for v. And with this equation, I can calculate what the disturbance or how the disturbance should evolve. So if I just write down these main points, so this is an equation in V. And of course, that also means if I can solve this equation for V, I can directly calculate also, for instance, the u velocity. Because I know there's, of course, the continuity equation. So that means in 2D, I can actually use du dx plus dv dy being 0 to calculate u. So I can integrate and derive and get the velocity u out. The equation is homogeneous. So that means there is nothing here on the left, on the right side. So it's homogeneous. Which of course makes it then quite straightforward also for an eigenvalue problem. Or already now you can kind of get the idea that perhaps there is an eigenvalue problem for V, because of course one solution here would be V being 0, but of course that's only the trivial solution. So all the other more interesting solutions will actually be eigen solutions to this problem. The last observation that we can also make, that in 3D, of course, then it's not so simple to just use the continuity equation to also get the W component. In 3D, we actually need a second equation. And for that, and we do that after the break, for the second equation, we would actually use the wall normal or the y vorticity, which we can call eta. And that gives us then in the end something that's called the V eta formulation, where eta is defined as the wall normal derivative, omega y, which is du dz minus dw dx. The reason why we take this, and we will write that down after the break, the reason for that is that in 2D, this eta, this vertical vorticity eta is actually 0. So that means that if we look at a 2D problem, this additional equation that we would need for the three-dimensional disturbance is actually identically 0. So we don't have to consider it. So in 2D, this eta is 0. Okay, but with this, let's take a break, and then after the break, let's analyze all these equations a little bit more in order to also understand what types of solutions we can get. Okay, so let's have a break, and then we continue in 15 minutes.